In this tutorial, we will perform propagation simulations for the Y branch using the 2.5-dimensional finite difference time domain solver in numerical mode solutions. Please note that there are many details required to obtain accurate FDTD simulations. This tutorial only introduces the basics. I recommend going through the scripted example, which lists all the steps. By having a script, you can read all the steps and be sure not to miss any critical steps or parameters. We begin by importing the mask layout GDS file for the Y branch. We set the material to be silicon. Then we edit this object and set the silicon layer to be 0.22 microns. We add a simulation solver, this time the variational FDTD solver. The simulation region is the black region within the orange boundary. We move the simulation boundaries so that the boundaries cut through the waveguides. The software will automatically extend the waveguides beyond the simulation boundaries. The solver uses the effective index method. The green X needs to be placed in a region where the waveguide is present. We add a mode source. This will inject light into the waveguide, and we place it at the input waveguide. We set the wavelength to start at 1.5 micron and stop at 1.6 micron. Next, we check the FDTD settings. We look at the mode profile in the slab. And this is where we had previously put the green X. We note that the default settings do not consider a very large span in the wafer normal direction. Hence, we want to increase the geometry. Let's change the Z span to be 2 microns. Then go back and plot the slab mode profile. Next, we edit the source. And let's check that indeed it does look like a TE polarized mode, just like in the effective index method. Next, we're going to add a monitor, specifically a frequency domain, field, and power monitor. We edit the monitor. We want it to be a 2D X normal monitor to capture the field profile and the power at the output waveguide in the cross section. We move the monitor to only capture light in one of the waveguides. Next, we check the material settings. We see that the material for the simulation is not silicon, but rather has been replaced with a new material called core material. This material is the effective index of the slab waveguide, which is 2.8 in this case. Finally, we can run the simulations. Because this is a 2D FDTD simulation, it is very fast. Now we can visualize the data in the monitor. T is the transmission versus wavelength plot.